for today. We have two nice papers in this session. The first paper, before we start, actually, service communication, I remind you that if you have any question, you can just type a Q on the chat, or you can just write your question and I will give you the word for asking the question yourself. So the first paper in this session is OTOSO. Not sure how to pronounce. Florian will tell us how to pronounce that. Online trace ordering for structural overviews. That's a nice paper about essentially visual tools. I mean, tools that can also be used visually to identify hotspots of what's going on in the stream. Florian from LMU Munich will present the paper. So Florian, I will stop sharing and then you can share and start your presentation. Floor is yours.
Maybe now. Can you hear me now? I hope so.
Now we can, and we see your screen.
Perfect. Perfect. Okay. So thanks again. Yeah, I will present OTOSO. You pronounce it right. Actually, there's not a right and wrong. So we write it and didn't think about pronunciation, but it's fine. Yeah. So it's a visualization tool, as you mentioned, and we thought about the following problems. So imagine you have a process. Here it's a very abstract process. So you have a factory and you want to have some bags, and you are producing, for example, blue bags. And at some time, you have suddenly a red bag in front of you. This is a representation for drift in the process. And now what to do? Well, you first think of a simple solution, of course, and you just paint it blue, and then you are fine. And then several other things in the factory happen. So at other assembly lines, also red bags appear. Which is referring to concept drifts occurring in the whole process environment, in the whole application. So what to do now? Well, simple solution version 2.0 would be repainting them all. This is feasible until some other point in time. When you arrive at this point where you have only red bags, there are some blue bags left, but apparently there had something changed, but you don't know why and what and what to do. So you have to rethink the whole process. So this is tedious. You have to come together. You have to collect smart people, what to do next. And well, they came to a solution after some time. Well, take all the red bags, don't repaint them because it's too tedious. Put them just in blue, in yellow boxes, except the previous ones were just put in green boxes, and we are fine. We can just ship them in yellow boxes, okay? Then you re-implement this, change the whole process physically, and then you come back to your assembly lines, and this happens. So the drift, the anomaly just vanished. There's nothing left. Now you are left with a lot of yellow boxes, and you have a problem. You have a lot of expenses and don't know what to do. This is roughly an abstract description of what the problem is, what we are dealing with. So having drifts and having anomalies, having dynamic clusters in your event streams, you have to get a feeling for them very quickly to decide whether you want to have some sophisticated solutions or you want some cheap solutions, some quick solutions. And to get this feeling, you need a good visualization to know what you're dealing with. For us as researchers, we also want to know about data sets. Are there some clusters we can detect? Are there some anomalies? Maybe the anomalies or the drifts are not in the complete data stream, but only in some parts. And to have some feeling about the ground truth and to look for a ground truth in the data or to look for the things we want to detect, we need to get the feelings at best with the visualization tool. And that's what we are doing now. So I will start with a short recap about the essential parts of our method. So there are, first of all, the temporal deviation signatures we proposed in the previous paper. It's very simple solution to track all the temporal differences between two activities within a case and doing some set scoring, putting them together, having zeros for the unseen activity pairs, and then we can vectorize all the case data into some equally shaped vectors and can move on with data mining techniques. The next thing we need is density-based clustering, which appeared to work really well on this vectorized case data. In density-based clustering, you are talking about densities, which are defined by having some points, which is the min points variable, within a neighborhood of size epsilon here. So you have these two parameters, which together define the density value of a data set or of some point neighborhood. And then you can classify, actually every object can be classified into one of these three categories. Either it's a core point, if there are at least min points, many points around in this epsilon neighborhood, or you can at least reach a point or a trace or whatever object you have within an epsilon range. Then it's a border object. It's at the border of a cluster, or all the remaining points are just noise points. And then you are left with three classes of points, and you can go on. There's another tool, which is optics, which is based upon this idea, and it orders all these points or objects in a two-dimensional plot. Two-dimensionally makes it very easy to visualize things, and it's also a thing what we are doing later, but we don't using the optics plot itself, but an adaptation of it. Nevertheless, two-dimensional plots are really helpful to visualize cluster structures. However, optics is only suited to give us a snapshot for one static data set at one point in time, and we have to use it to visualize a whole data stream for the whole duration of the stream. So that's optics. Here's a more visual interpretation. So if I have, for example, these three blobs, the green one in the left bottom corner is a little bit separated, and this is visualized in the optics plot by this peak in between. And the blue denser area on top, on the red one, is causing a deeper valley within the red cluster representative in the plot. So this is the kind of way you are reading an optics plot. So we will start with the actual working steps of OTOSO. I will repeat them later, but let's start with our hashing method. It's nothing new. It's cuckoo hashing. We didn't invent it. We just use it. But it has some beneficial aspects which are useful to get this vectorized data later on. Cuckoo hashing works, if you're not familiar with it, with having two potential storage positions for each object. So you can use the standard hash value in Python, for example, just turn around the case identifier and then use the same hash function again, and then you have two positions possible in the hash table. So it's technically not that complex. We use per position some buckets here. We will show later on that it's advantageous to have these bucket positions. It decreases a little bit the speed or increases the complexity, but it makes up for a better hash table recency management. So if we have a conflict, then later on we will have a lot of conflicts because the hash table will be full at some point in time. We have to swap out old ones and rehash new ones. And this is just done by taking an object where the conflict happens and trying to rehash it into the secondary position. There will much likely also be a conflict. Then we have to cycle around. So taking from each of these rows the least recent one, rehash it at the other position, find there the least recent one. And after a short time, it's usually really a short time, the cycles don't last very long, we can discard the oldest ones, and then we are fine, basically. The thing I'm really, why it's important for me to show this hashing technique in the paper as well as here is because of the log sample fairness, I would call it. So if we just give a random number for each case and say, well, if the random number is beyond 0.5, we will put it into our temporary structure where we collect all the cases, or if it's below, then we just discard it. This will benefit, for example, rather the shorter cases. So if we have a lot of short cases or just beginning cases, which have a lot of speed, a lot of momentum. They will just come in our stream and we store it. They will over some time somehow overcome the rest of the cases, which might be more interesting, which have larger durations, which are more complicated, for example. This leads to putting more emphasis on the cases which are just shorter and easier to process in many applications. This solution is not perfect. I think the problem of sample log fairness is much more difficult as that we can handle it in just one paper, but we can maybe later discuss on that. So I will just go on. Then we have this sample of a log, which is more or less fair. And we are applying this temporal deviation signatures on this sample. We are ending up with just vectorized data. And for all the stored cases, we have one row in this matrix. And for each activity pair, we end up with one column. So, and this is finite data, so we can also apply optics, which is not a stream approach in its naive way, but as we have finite data here at this point, we can just apply optics. And optics is then used to define a cluster level, so a neighborhood size. This epsilon variable is used at one point. So, for example, here's 0.1, and if I cut all the curve intersection parts here, I can separate different clusters from each other. So I said the valleys are the clusters. And for example, here in the first one, in the left one, there is one large cluster here because there's just one area below this threshold. On the second one, we have a second cluster establishing at some point in time. It's actually the same data set. It's just a later point in time where this where the window leads to this plot here. So there are clusters which are emerging later and then disappearing at some point. I also have this this ground line at 0. At 0. This is actually caused by cases in our hash table which just consist of only one activity. Then there are no relations of two activities, and then the whole row is just 0 in the vectorized data. So then I have different optics pictures, optics figures, and then I can derive some data from them and put into another visualization. So I have this time stream here on the lower part of the slide, where I have different blobs here. Each blob refers to one valley in one optic plots above. So if I have, for example, the 50K here, there is a large blob below, and there are two smaller ones above. And this refers here to the first picture where I have this large cluster in the middle. There's a shorter one here, and a mediocre sized on the left part. And this is the blob size is just referring to the size of the cluster. So the size of the blob in this visualization makes up for more objects, more traces within a cluster. Then the next thing is the height is referring to my density. So if I have a lower density, the cluster will be more below. And for process data, it's rather natural to have a lot of large or just one large cluster at the bottom, because there's some baseline process going on. All the traces which behave very well, which behave to some normative, to some standardized model, will be present in this large cluster. And then the more anomalous or the more deviating clusters, which might be smaller, maybe non-conforming traces only, will tend to have a lower density just at the edge of the data set. So, and then I can also connect the blobs by using their representation. So if I have a cluster, I can check where the attributes are. So what's the temporal deviation signature like, and then compare the signature just by using Euclidean distance, for example. And I connect them if they are below a threshold, and I can see the relation between different clusters over a span in time. So in practice, we try to evaluate on the recency of the hash table and trying to find out what's a good ratio between using a larger hash table, maybe only one-dimensional. This is the green line here, for example. It's always the green label. And then we are introducing some buckets and decreasing the length of the table. So having the same amount of objects in the table, but another ratio of width to height. And we see some buckets make it more recent, the data in the table, having a lot more. So for example, 100 positions for the table, but having 100 buckets per position is not really a big advantage against the previous ones. If I increase the number of buckets, I lose the advantage of the hash method, because hashing is really fast, but going through this list in each position is not a good idea. So I think having some buckets, that's the takeaway of this slide. You should use some buckets, but not too many. It's just a rule of thumb. Okay, then applying it to a data set, we use the BPI challenge data set of 2017 because we knew from previous experiments that there is a cluster. You can see it, for example, in one snapshot here above. There is a large outlier cluster here. It refers to some of the accepted offers. And the accepted offers have a lower, they are processed, not all of them, but some are processed really slowly. And these traces make up for this outlier cluster. We try to apply it here, and you see in the beginning there's some mess around. It's just a streaming method. I think most of the streaming methods will have some messing around in the first n events. Later on, we have this cluster here, a black line which goes up, and here we lose it. But we find out it's not that this cluster vanishes, but the cluster is more overshadowed by the rest of the data. You can see it here above. We have all the cluster members here as a blue line, and the remaining cases as a red one. And we put the kernel density estimation here to see that the density of the remaining cases just increased here. In the rest of the data set, it was more or less equal, but then the normal, the conformant cases were just increasing over this time, and then we lose the track of this cluster here. So this might be a limitation of the method, and we have to see what we can do about different or deviating arrival times of events. A lot better worked it on the BPIC 2015 data set. We have these 5 data sets here, 5 sub data sets, and also in the challenge workshop, I think there was also some papers about that there are certain data sets in this complete data set which having a slightly different process model and different execution times than others. So we put all the 5 data sets together, concatenated them, and just concatenated this 5 times data set 5 times again, so ending up with 25 data sets and indicating it with the red lines here. And then we just applied our method. Again, after an initial phase where some things are messy, around 10 times the size of the cuckoo table. This is a good rule of thumb we found out. Then things tend to stabilize, and we have this connection here that the data set 1, 2, and 5 are more similar than the rest, the third and the fourth one. And this is actually what we are really happy to have here and to show here, because it's actually what we wanted to show. There's also an outlier cluster above, but I don't want to speculate what this is about. There's another behavior, but we don't have enough data to get, and we also don't have experts. Maybe if you have the expert, ask them what this small outlier cluster is about. So limitations, we have some parameters. The cuckoo table size gives us recency versus robustness. If you like either or the other, you have to decide what your table size should be. What can you do technically? What is the limit of your storage? Then we have, of course, our density parameters, the min points at epsilon, which is a tough data mining topic itself, and I doubted that we will solve this problem in future works here in this workshop or in process mining, because I think data mining community is working on that a lot of for some time now. Then the optics is not fully utilized. There are a lot of informations in the optics plot, and you could argue that, of course, we could also just use the dB scan, for example, as we only using one level of this epsilon neighborhood size. And you're right, but there are some other aspects we can use from the optics plot later on in future works. And I want to advertise that Ludwig is presenting on Friday a work where we show how to extract anomaly information from the optics plot and not cluster information. And this could also be interchanged here really easily. Then, of course, the trace sample fairness is limited. I already talked about this. And yeah, we have no adaptation to dynamic arrival times. This means that, as I showed for the BPIC 2017 data set, that in case that a cluster or the arrival times of traces from this outlier cluster stay constant, but the rest of events just arrive more frequently, then we have a problem to get everything yeah, evened out in the visualization. But I think that is something we can work on. Yeah, and here a visual summary. So these are the 4 steps we discussed so far. We have this collection in the hash table, deriving this vectorized data from that, determining the optics plots for each of these vectorizations. And then for each vectorization, we are plotting this relational visualization where we connect the relating clusters and having this time scale on the x-axis to allow for a quick overview where are plots, where there's a plot, of course, where are clusters, where are clusters emerging and disappearing, where are drifts, for example, when some clusters stay constant for some time and then change somehow, increase in size and so on. So there are a lot of things you can detect there. Yeah, and now I'm open for questions. I hope there are some. If there are not, I have 2 questions myself. So I would start, I think we should start with other one's questions.
Yes, so thanks, Florian, for your nice presentation. I see that Bas has already a question, so please, Bas, go ahead.
Yeah, thanks for this very nice presentation. I liked it a lot. I have kind of 2 questions. So first one is, could you elaborate a bit more on the use of the cuckoo hashing, in the sense that, to me, it seems that you want to somehow get a sort of a fair representation of the stream as a whole. So in that sense, would your algorithm still work if you would just simply use a sliding window, or is that really not working?
No, it's really working. You can also use another, so just a sliding window, as I think Ludwig also used a sliding window before. This would perfectly work technically. It was just that we thought about having more fairness. So if we think about also including traces which are more anomalous, and these don't tend to be the majority of cases usually, we have to make sure that we don't lose them in the sampling process. If we just using a sliding window and putting just events there, and there are enough events arriving in a short amount of time, then we are just discarding the cases which take longer. So we just concentrate on starting on the prefixes of cases and never see the end timestamps or the end activities of cases.
Yeah, I see. I definitely see that. Okay, thank you. Second question is more like, now you're focusing a lot on temporal distances, but is it fair to say that your whole approach could be generalized and you can basically measure any type of distance metric you would like? Because I would be extremely interested to see if there exist certain control flow characteristics that you can then again visualize in this this plot and to see how that evolves, basically.
I'm pretty sure this is also possible, but if you have the control flow, maybe you are exchanging the temporal deviation signatures by just a footprint matrix. Then you have this ones and zeros or threes and so on, and then the data is rather discretized somehow. Maybe then the clustering method wouldn't work that well. Maybe it's better then to go, instead of the optics and the DB scan approach, using some frequent item set mining, because this is more suited for this type of data, and clustering is a little bit on the top or over the top for using this type of data. But yeah, it should work as well, and we should try it out. Yeah.
Okay, thank you.
I see that Marwan also has a question. So Marwan, please go ahead.
Thank you very much. Yeah, thank you, Florian, for the nice talk. So efficiency is always an important issue for me, efficiency, when talking about density-based clustering. Do you think that you can apply streaming density-based clustering algorithms in a way?
Yeah. We actually thought about that, and I had an approach in my backend, but it was not enough time to really apply it. I presented it last week, I think, on another conference. Actually, yes, you're completely right. It's not a problem here because we only have a finite number of items here. So optics is fine, but the complexity of optics is not really nice if we have really a stream approach. There are already streaming approaches, and we also invented one for faster detection and a more abstract visualization of optics itself. It's called MTIX, and it works in correlation with that. I think it should work, but yeah, there was just not enough time to try it out here.
Awesome, congratulations. Great.
Okay, I also have a quick question, Florian, maybe. So I really liked your work too. And in your plot, in your OTOSO plot, I guess this is what it's called, you always plot the average cluster sparsity on the y-axis. I was wondering whether you can actually plot other dimensions as well in order to understand not only that there are deviations, so that there are new clusters or that the clustering is broken somehow, but trying to understand the root cause for that deviation. Can you do that?
Probably yes, but have you some dimension in mind?
For example, the type of items or the location, for example, the country where these events are coming from, or I'm now thinking country where GDPR has become into place as opposed to countries where this has not been the case.
I think it's a good idea to embed more information. You have to be careful to not embed too much information here because it gets overcrowded. Actually, also with the edges connecting different clusters, this is also something which is difficult to set because if you put too many edges there, it's just messy and you don't see a thing. But
another perhaps could be the cycle time, for example. So the average duration of the trace. That's something that typically you always have. Yeah,
I think actually, especially with this temporal information, there are a lot of aspects. So temporal dimensions behave more or less not the same than the control flow perspective, and there might be also some more abstract things which we have to keep in mind there. So to have some weekends and work days and
exactly.
Yeah.
So and then connected to that, the second question is, to what extent you see this plot as the final product, or final product, let's say, to give to the end users, or to what extent do you see these as an intermediate tool towards something more?
Primary, I still only have us researchers in mind to have as users of this, because we need a tool to just fast or quickly analyze what the data set, I don't know, the BPIC challenge 2021 will be in a short time. I don't know if it's really capable of giving some analysts this plot. We have to try it out and get some opinions. We didn't ask or do any survey on that. Yeah.
Okay. Thanks a lot again, Florian. I don't see any question on the WOVA or the
Yeah, I think
Zoom,
the time is over, so I will skip my questions.
Right, you also had a question for yourself.
No, not
you
for
can
myself,
take it offline.
Actually for the audience, but no, it's fine. I will do it later.
Okay. Probably you can just post it on the chat and
yeah, exactly.
Okay, so thanks again, Florian. I think we can move on with the second presentation for this session, which is actually from the same group at LMU in Munich. And Andrea Maldonado will present the paper, Performance Skyline, Inferring Process Performance Model from Interval Events. And in this case, we're actually talking about performance mining, essentially. So Andrea, I guess you're ready. Are you?
Sorry, I was muted before,
yeah.
but I am ready. Thank you so much.
Okay, so please, the floor is yours.
Right? Okay, thank you. All right, so hello everyone. My name is Andrea Maldonado, and it is my pleasure to be here to show you, to talk about the performance Skyline today. So let's get into it. I think the agenda is pretty self-explanatory, but let's, yeah, as Andrea said before, my topic is also concerns time, although it's more of a performance mining topic. And the time perspective for our approach is as follows. We have traces that have a start time and an end time. This is also, this duration is also called lead time. And other than that, in some traces, as the one here, you might have some pauses where the events are not actually being executed, but are waiting or are in so-called synchronization time. So the waiting synchronization time for a case is the lead time minus the service time. Although this is then on the overall, or this is overall the whole trace, and not only activities or events where we might be also able to speak about duration, but more on that later. First, let me tell you a little bit about the data set that I also use for in the investigation of our approach, and where we have this use case that I also use as a motivation. So imagine that you are at vacation, sadly towards the end, and then you decide that after this vacation visit to your favorite city, you will write a review to rate the hotel where you stayed in. Then this is then processed by pipelines as the one of TrustU GmbH, which is a German guest feedback and hotel reputation software company. In a process pipeline called as this one, which in this case was called daily. What it does is that it takes and ingests several reviews from multiple sources, and then makes some transformations and some aggregations on them, so that at the end what you have is an accurate rating of a specific hotel. In the interest of hotels, it is to have an up-to-date result whenever a new review is coming in. So because, well, your decision or the decision of a guest to stay there or not has a high correlation with the revenue. All right, so if you have a data pipeline like this, and you might want to reduce the overall duration to keep it running as often as possible. In this one, we started with an overall duration on average of 48 hours, so not quite daily. And what you do when you look at the possibility to improve the performance of a process is to then start running at activities that are sequentially in parallel. To evaluate what kind of changes are possible, you look into the interdependencies between these activities and events. And to then evaluate which of these activities or which of these changes have the highest impact on the overall duration, you might want to also look into waiting times and service times as described before. Some challenges that come with this are the high amount of events, since one of these pipelines would have normally over 12,000 events distributed over like 200 activities, which might, if you are aggregating over several days, within time you get a big data set, and you don't want to look into like every single activity. Another challenge is that the service time of a certain activity might deviate. So we have activities that will on average take 5 minutes, others that take 5 hours, or some activities that sometimes take 5 minutes and sometimes takes 5 hours. So lucky for us, in order to answer many performance questions, there are several performance analysis tools. And what we will be looking at is how to find the dominating events or dominating activities regarding performance. Before we go there, I also want to mention that other motivation purposes, furthermore than process optimization, of knowing then the duration of activities and filtering the most interesting out, might be also the proper usage of the resources that you have, and also to take informed decisions on how to order your tasks best. So overall, what we want is also to look into events that are not only entailing a single timestamp, but multiple ones, so that we can really speak about real duration. In the field of performance analysis, there are several techniques that already do something similar or that already concern themselves with some interval events. I classify them here in 3 flavors and some in between, where we have some approaches that are specific to certain performance features or performance questions, as finding bottlenecks, concept drifts, and so on. Others that are flow analysis based, and others that are primarily to analyze cases and compare cases to each other. The limitations of even though they do very well what they do, they all show at least one of these limitations. For example, being control flow based, they then have some assumptions of all the activities lasting the same amount of time, or they very easily overflow the visualization when you integrate even more data as more timestamps. They also sometimes they're also limited by the knowledge that you can get out of one timestamp, or having only sequential activities, so nothing running in parallel, or not considering some analysis of the cases on case level, so regarding several activities. Also, the constant and this assumption of that all activities last the same amount of time. All right, so in the spirit of two-dimensional plots are easy on the eyes, we take the Skyline operator, which again, thinking about vacation, when you will decide which hotel you want to stay in, you might use the Skyline operator to find the best compromise between, for example, here, price and the distance to the beach. So you might not want to take the top left point, which is very expensive, but is very close to the beach, and maybe you don't want to take the cheapest hotel, but might be very far away. So if you want to investigate which are the points that are most interesting to you, that make this compromise between them, you want to filter all the hotels out and just take those, you use then the Skyline operator. Since we are interested in the performance of processes, we want to look at some kind of filtering that gives us then the activities or the events that perform the worst in terms of duration. I will tell you more about this later. For this, we already know duration. We need then 2 timestamps, and for this, we then define the interval events as follows. In our case, we have, as we all know, the case ID, activity ID, and timestamp, and now we have an additional timestamp so that we can mark corresponding the start and the end of each activity or each event. Right. So on the other hand, we have the geometric interval representation, where what we have is here a schematic representation of several intervals, for example, here A, B, C, and D. And what we do is that we plot these intervals into a 2-dimensional space, taking start time as a horizontal axis and end time as a vertical axis. So let's start this procedure by taking, for instance, interval A, where we have it starting at timestamp 1 and ending at timestamp 3. So we plot this in our 2-dimensional space, and it looks like this. If we then follow the same procedure with the rest of the intervals here, A, B, C, and D, we end up having something like this. All right, so now how we do, we're almost there. We're almost at our traces from process mining. So we have now, we could say now that each of these intervals are also events, and the A, B, C, and D could be the activity IDs. So what is missing is thinking about the link between these points to represent a trace. And what we do here is that we then draw a line between the points representing that they belong to the same trace and by the order of the starting time. All right, now for this toy example, you have 4 events, so it's quite easy if you would like to look into the performance of each of them. You can, but if you want to take some traces into account that have several thousand events, you might want to filter them out. And for this, we use the Skyline as before, coming then to this performance Skyline. What we do is we want to take the events that have the longest duration. That means they start the earliest and they end the latest. So in summary, we want those events that are the closest geometrically to the top left corner. In this case, we then have B dominating on C. In terms of Allen's algebra, interval algebra representation, we can say that B contains C, and these are the, so if an event is contained by another one, that does not, it's dominated, and thus it does not belong to this performance Skyline. So we ran some experiments and to do some investigation of this performance Skyline on real data. And here is the visualization of a small snippet of the first 2 hours of running, of this process called daily, where we then used first the geometrical representation, sorry. And here we can already see that there are some, we see lots of traces that are represented by different colored lines, and the color of the points are regard than the different activity IDs. Even though you can already see here that there's some peak on the activities that are depicted in this red pink color on the left, and maybe some here on this often this blue color on the right. Other than, and maybe you can also see some patterns of activities that repeat themselves. Other than that, it is pretty chaotic and it's not so easy on the eyes. So if we filter out actually only the performance guidelines of those activities, taking only those that dominate others by duration, we end up having something like this. And even though we still can recognize some kind of form there, it is, if we want to generalize and if we want to create some expectation to compare against later to say that a trace is conformant or not, it is suitable to then use different statistical analysis techniques that I will then present to you next. I won't go too deep into the math, but you're very welcome to read the paper for that. The first one is the average trace Skyline. What we do here is that we compute the average over all traces for specific activities, and it looks like this. This works well for this data set since we have always the same activities that are appearing in the same order, and the variation or the variating actually happens in terms of performance and not so much in structure. So this is what we see here. And then what the average trace Skyline does. So we have the average trace and then we compute the Skyline, which is on the right side. And then we already see we have like the top 5 activities that are the most interesting ones in terms of duration. These are the ones that last the longest in comparison and dominate the others in comparison to the points that you see below that line. The misadvantage of taking this approach is that you might exclude some activities that would be in the performance Skyline for some traces, but do not appear in the majority of them. So they're omitted and they're not part of the performance Skyline over here. In order to have a less restrictive view on which activities to take into the performance Skyline, for this generalized method, what we can take a look at this average Skyline trace. So you might have noticed the only thing that changed here is the order between Skyline and trace. And this is sorry, between, yes, skyline and trace. And this is because what we do here is that we first compute the skylines for every trace, and then afterwards look into the average of them. So what we have here is every activity that is on any trace part of the skyline, it's then represented in this then average trace over all skylines. The advantage of this one is that you are including all the points that are that some point are part of a skyline, which makes then a disadvantage, which is that it is then very prone to outliers. If you want a good compromise between both of those, you might take a look at the expected activity set. The idea here is that we take all the performance skylines of all traces, and then we look at the appearances or the probability of an appearance of a certain activity in all these performance skyline activity sets. And we end up having something like this, where what we see is that this update crawl start task was always part of the performance skyline on this data set. All right, with this, I then mainly go to the takeaways. This is a very generalized method to build on that offers a new perspective to build on for further performance analysis on the multi-timestamp view. It also, I think for me, it also is a takeaway how combining different things, for example, in this case, the interval-based sequence pattern mining of the geometrical representation and some process mining techniques, we can end up having something new that offers new insights into the processes we are looking into. Other than that, we also gain, using the statistical analysis techniques, some performance knowledge for generalized representations of processes here that we can then use for then later conformance checking or detecting and discerning different patterns on these visualizations. Yes, we did some exemplification and investigation using these real data sets that had this start and end timestamp. And the takeaway here is, if we have that information, why not make use of it? You can also find all of this information and how it was implemented on this GitHub repository. And yeah, as I said, this is quite, I would say it's a new perspective to build on. And this is why the future work, as you can see, is a very full slide of stuff where I see first some variations would be that might be interesting to investigate, include some implementations of the different implementations of the Skyline operator, looking at other dominant features, so maybe not the dominant duration of activities, but taking waiting time into account, or something that is not even time related as memory usage. Also building and investigating streaming interval events, since this is a daily pipeline that is rather executing or analyzing data in batches. Maybe streamifying would be a keyword there. Then other than that, in the fields of process discovery, also this could be used then to identify loops and choices, see how see how this is visualized there. Also extending and enriching this visualization with some other items, as I mentioned before, including waiting time, including memory usage, and so on. Adding maybe also a third dimension to not lose the knowledge about the duration, but then rather enrich it, or have done more information about dependencies also being included. In the field of conformance checking, we can also start doing some clustering, anomaly detection, or other recognition of patterns, as well as prediction tasks. And last but not least, also in process enhancement, recognizing bottlenecks, or using some probabilistic pattern knowledge for detecting some how to allocate resources best. Then, for example, using expectation maximization or other approaches. As you see, the list is very long, and I would be very happy to now listen to your questions and have some feedback from your side. Thank you so much.
Thank you very much, Andrea, for your nice presentation. And yeah, this novel approach, it seems very nice and very promising. So any question? Let's see, please write a Q in the chat so I can give you the word. Maybe, Bas has already one. Okay, so Bas, please go ahead.
Yeah, thank you for this interesting presentation. I have also a question. So I was a bit lost how to exploit the Skyline to effectively improve process, but I can also understand, given that one of your future works is to still go for this bottleneck recognition, that is kind of also an open area. I was in that sense, I was thinking a bit that let's say if you could classify the instances of your process, meaning that I have groups of traces that somehow are similar. Even you could say, okay, every trace is a class. Could you then also exploit this for, let's say, prediction, where you would say, okay, this certain trace belongs to that class, and this is the, let's say, the historical skyline. So you kind of already know, okay, usually this activity is going to be here and there, and to already say this is running faster than normal, or this is running slower than normal. Have you thought of an application scenario like that?
Yes, definitely. Thank you very much for your question. So as I wrote here also as part of future work, anomaly detection, not only then on trace level, but being able to see, okay, if this trace belongs to this trace class, then, and now we have maybe some, or some cluster on behavior of performance behavior, let's say, and then you get another trace that behaves differently, but it's supposedly then also belongs to the same class, saying, okay, not only this is an anomaly, but also looking into a finer granularity level and seeing, okay, this is not only an anomaly, I'm able to say this is an anomaly since like this activity is now behaving differently, or since this one also behaves differently, all dependencies are also rather in the back or performing, or maybe there's some unexpected set of the activities that now dominate the others in terms of duration. So this is one of the approaches. I also started some experiments on that, and so it's rather on the, let's say, continuing future works, or that the ones that have continuous. But definitely, thanks so much.
Okay, thank you, Andrea and Bas, for the question. Let's see if there are other questions. Otherwise, I would also like to a bit hook or continue this question, because you have seen two ways of calculating the skyline. And I was wondering if it's possible to apply other operators to the skyline. For example, calculate the skyline of the maximum time. Or so could this be a good direction towards identifying these bottlenecks?
All right. So, for example, if I'm sorry, I might rephrase it just to make sure that, just to confirm that I understood the question correctly. So you say maybe applying some other operators instead of looking at maximum duration as we are seeing right now, maybe looking at the minimum duration, or I think do this. Yes, it is possible. For me, it's also a question what would be the target, or what would be the purpose if we look for the let's say the minimum duration path. We would kind of look, okay, these are the activities that we're doing very well, or still we could use this in combination of with knowledge of resources to say, well, this might be if there are some resources that are focusing only on doing this activity that are being completed very fast, we might be able then to say, okay, then maybe stock some other activity or combine some activities into a new one for that resource, so that we have more equilibrium into the charge of the whole process into the resources. So definitely I see some potential there. Another thing that I think it would be very interesting to integrate into this performance knowledge is the dependencies on some way, either with a third dimension or something similar, to see then also how this would behave, not only then with dominating duration activities, but then we would be also talking in terms of the critical path analysis, where you also need the dependencies into to take those into account.
Yeah, thank you.
Thank you.
Maybe if I can ask another question, which is about the future work that you mentioned about streamifying. I think you used this word, this term. So could you mention a bit how would you see that? How would you, if you have thought about that, any idea of how this could be done?
Yes. So to be honest, I have given some thought on this. I think first this process that was presented, or that was where I got the trace set from, where we had also these 2 timestamps, that is kind of the condition to use this method itself. I mean, we can also take assumptions as in, well, the next event is the end of one event is the start of another one, but then we disregard the waiting times. Well, using this, I think if we would have done or processed the reviews, not as a batch of reviews that we then daily process, but more of a stream, then we would also get this kind of logs. We then could speak of a sliding window and see how to sample the logs best. So then we could also go into the concept of, we could also take a look into concept drifts. For example, I think now in the times of the pandemic, as it was mentioned before, this has had a big impact into our models, and especially talking even in this use case on the hospitality industry, where maybe the review amount was decelerated, but not even in taking this pandemic into account, but also some cycles, as when people, as like this summer break where lots of people go into vacation, then you might have a higher load of reviews than another time. So I think these are some of the challenges or questions that rise when you would approach then streamifying this approach.
Yeah, I think it's also probably very useful to use this Skyline as you mentioned, as one indication for drifts occurring. So you can use this as a feature, let's say, for a drifts identification algorithm. Yeah.
Yes, thank you.
Okay, I don't see any further questions, so I think I would like to thank you again, Andrea, for your presentation. And this was the last presentation of the workshop. Thanks a lot, everyone, for attending. I think we had a nice pool of papers, and with some very interesting take-home messages out of that. I think, at least for me, the most important take-home message is that stream mining and stream process mining in particular is still quite challenging, which I think is a very good news for researchers. There are many problems in there. I think things that we discussed about today are drifts, concept drift in general. The identification of this drift is a pretty challenging topic. Parameters tuning is also a very challenging topic, which is not solved, and to some extent also the problem of approximation. So I think there are very interesting takeaways. Marwan adds anomaly detection. That's probably another important keyword out of the trace clustering. Yeah, there are many take-home messages. So thanks everyone for participating. I don't know if Bas, Marwa, or Thomas, if you have anything that you want to add. If not, I think the conference continues in about 15 minutes with the contests. So yeah, I think that's it. Thanks a lot for tuning in. And Marwan, do you want to add anything or no?
No, I just want to say thank you very much for the participation and for the presenters, and of course for the organizers for this good job.
Yes, thanks to Mirko, who has been checking that everything went smooth. And
yes, of course, yes. Yeah, thank you.
Thanks to you.
Good. Okay, so see you this week in some other workshop. Bye-bye.